Basic trig functions. Sine, shortened to SIN, but you still pronounce it sine. Opposite over hypotenuse. Cosine, adjacent over hypotenuse. Tangent, opposite over adjacent. If you have learned it any time at all, you know that this little acronym here. SOHCAHTOA. All right, opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. Your reciprocals, no, they don't make sense. I didn't make them up. But the reciprocal of sine is cosecant, and the reciprocal of cosine is secant. Why they didn't just make them both co, and I don't know, but they didn't. So tangent is cotangent, but reciprocal just means flip those ratios, right? And so this is all relative to what angle you're talking about. So when you get a right angle trigonometry problem, the number one thing you need to make sure is that you label it correctly, okay? Hypotenuse is easy. He never changes. He's the guy opposite of the right angle. But the other guys are relative. If I am talking about A, that's going to look different for those three trig functions, or three basics, there's 6 altogether, than it would for B. Because for A, opposite is if I were to stand in this corner and walk across the triangle, that is opposite. Adjacent is the guy that makes up part of the angle. All right? But for B, opposite's going to be over here, and adjacent's going to be here, okay? And so make sure you label it correctly. It will mess up all of your trig functions if you don't, all right? Finding it's really simple. If you look at example 1, evaluating the trig functions, they want all 6 trig functions. The only thing here is they left out one side. Thank goodness we know a theorem to help us solve for one side of a right triangle. What is that theorem? There we go. A squared plus B squared equals C squared. I pulled this little bit because I actually do love math history. Pythagoras is credited with it, but Pythagorean theorem was used long before Pythagoras. This says, I mean, we have actual documentation. Clay tablets shows ancient Babylonians were aware of this relationship. When the Egyptians built the pyramids, they had to have known this relationship. Pythagoras, this would have been in these time periods, which was over 1,000 years before Pythagoras even came on the scene at 500 BC. So he's credited with actually, taking note of this is an actual thing that works every time and recording it. But we have records of them using this theorem for right triangles long before he's actually on the scene or born. But anyway, I just found that interesting. So yes, Pythagorean theorem, a squared plus b squared equals c squared. So what have they given me? They've given me one of the sides and C. For the Pythagorean theorem, it doesn't matter what A and B are as long as you get C correct, okay? So in this case, you could say like G squared plus 6 squared. Make sure the 8 squared is what's by itself, right? You don't get a perfect. I think you get square root of what, 28, right? Something like that. So it is not a perfect. Take the square root. It's always going to be the positive root, by the way. This is my third side. Typically, you don't do these in decimals because you're talking about ratios. So if they ask for the 6 trigonometric ratios, they do not want decimals. We will use decimals with trig functions, but when they're asking for ratios, give it as a fraction, which means you do need to rationalize that root out if it ends up being in the denominator. But at this point, they say 6 trig functions. You need all 3 sides to start. Make sure you have all 3 sides using the Pythagorean theorem. Then figure out which angle they're talking about. They're talking about angle G. That's this guy right here. You're going to label it based on G. Hypotenuse is easy. He doesn't change. Opposite, that would be my G. Over here, 2 squared is 7. 2 squared is 7 is my opposite side. That means 6 is my adjacent side. And then I just do SOHCAHTOA. The sine of G is going to be opposite over hypotenuse. We do want to reduce, right? My cosine going to be adjacent over hypotenuse. Again, we want to reduce. And my tangent is going to be opposite over adjacent. All right, to find the other 3, flip them, right? So for cosecant, I'm going to say 4 over square root of 7. Rationalize it. That's going to be 4 square root of 7 over 7. Secant, flip it, 4/3. Cotangent, flip it, 3 over square root of 7. Rationalize it, 3 square root of 7 over 7. Right? So, very simple. Special right triangles. Special right triangles are 30, 60, 90 and 45, 40, 90. When we build the unit circle, they're based off of 30, 60, 90 and 45, 45, 90 triangles. The whole unit circle is that entire thing, okay? And so these are ones that you need to know. You will use these over and over and over and over, okay? And so they give you the figure of how you get it. 30 degrees, 30 degrees. This is based on your side square root of 3, and your 2 times your side. So for 30 degrees, if I'm going to do opposite over hypotenuse, I will get 1/2 every single time for every 30-degree angle, no matter how large or how small my triangle is, because it will always be in these ratios. When I look at my cosine, I will get x squared root of 3 over 2x, which ends up being square root of 3 over 2. And then when I get my tangent, I will get x over x squared root of 3. I rationalize it. I get square root of 3 over 3. And then the cosecant, secant, and cotangent, you don't really have to memorize these because I can just flip these first 3, right? So if you will just memorize the first half of this chart, the last half are just reciprocals of the first 3. Know your sine, cosine, and tangent of these 3 angles, okay? 60, I'm going to go to 60 next because you'll notice that 60 and 30 are complementary angles. They add up to 90. You'll notice that your sine and cosine just switch places. The sine of a 30 is 1/2. The cosine of a 60 is 1/2. That's because you're on the other angle, right? And so it would match the opposite, right? The cosine of a 30 is square root of 3 over 2. The sine of a 60 is square root of 3 over 2. So you'll see how these guys just flip-flop. And then these are just reciprocals of each other, okay? This is square root of 3 over 3. This is just square root of 3. So your 30 and 60 relate to each other because they are complementary angles. Complementary angles will always do that. The sine of one will be the cosine of the other, always, all right? 45 is also a special angle. Remember, it's side, side, and side square root of 2. That's your special right triangle here. So very simply, your sine and cosine are the same because your opposite and adjacent side equal each other because it is an isosceles triangle, right? So your sine and cosine are both square root of 2 over 2. And since this guy is those sides over each other, you put the same number over itself, you get 1. Okay? So if you will just remember the sine, cosine, and tangent of these 3 special angles, you will, 1, know the entire unit circle, and you can get your other 3 trig functions from your reciprocals. All right? Particular thing says, given acute theta, where sine equals 0.8, find the other 5 trig functions. They make this a unit triangle, so they do like 0.8 over 1. I personally don't like that, okay? If I were doing this, 0.8 is clearly a fraction, right? Hopefully all of us can write 0.8 as a fraction. So if I were to say the sine of theta is 0.8, I could also write that as 8 over 10, which I can write as what? 4 over 5, all right? By the way, 4 over 5 is a beautiful trig function to get because it is a Pythagorean triple. All right, but let's say I don't know that. Let's say I don't remember that, which is fine. You can draw a right triangle. And you can say, well, let's just label one of these as theta. We'll say that this guy over here, he's going to be theta. My hypotenuse is here. My opposite is here, and my adjacent is here. If they gave me sine, which 2 sides did they give me? Right, remember SOHCAHTOA. They gave me opposite, that would be 4, and they gave me hypotenuse, which is 5. Pythagorean theorem every time will give you a 3 there as your adjacent. Now they want the other 5 trig functions, right? Well, you've got it. I mean, cosine's going to be 3/5. Tangent's going to be 4/3, and then just reciprocate them. 5/4, 5/3, 3/4, right? Does that make sense? And if they want it in decimal form, those are all beautiful fractions to put in decimal form. You hopefully don't even need a calculator there. All right? They did this with 0.8 over 1, and then they did the Pythagorean theorem with decimals. Personally, I would just put it as a fraction. Personally, that's how I would do it, okay? So once you have one trig function with fractions, you really can get the other ones if we're talking about right angle trigonometry. Now, when you start doing any point on the circle, then you have to consider, that's why it said acute, by the way. That's why it said acute. They are telling you this is a right triangle, right? Versus we can't have an obtuse right triangle. Why can't we have an obtuse right triangle? Because then we'd have more than 180 when we add up our angles, right? Because a right triangle can't have another one that's 90 or more. Doesn't make sense, okay? So when you're talking about right angle trigonometry, just put it in fraction form, and now you can get all 6 of them if you have one of them. Make sense? There we go. So this one was tangent of this guy. So cosine of 37, that's just degrees. Make sure you're in degrees. You can check by doing cosine of 37, right? If you get this little t tiny 0.7986, you're good. If you get something else, you did something wrong, or you're in radians, okay? So make sure your calculator is in the right one. If you hit mode on a calculator like this, the very first screen tells you radian or degree, okay? The next one. So the next one is, like I was saying, the 61 in 40 minutes. They did this whole conversion. I would just do 61 plus it is 40 minutes out of 60 minutes. All right. Make sure again that you are in degrees for this guy, and then just do tangent. It opens a parentheses automatically. Inside the parentheses, it will do order of operations, so you don't even have to worry about another set of parentheses. 1.85 rounded to the nearest 100th place, but 1.85 is going to be it. For the next one, pi over 6. If you are in degrees and you want to stay, you can literally do sine of pi. Well, it's, you know, your pi over 6 times 180 over pi. These cancel. You can just do sine of, 180 over 6, which is just 30. So hopefully you'll get 1/2 there. Or you can go into your calculator and change it to radians if you want to. Personally, with something this simple, I would just cancel out my pi's. And even if it wasn't a perfect 180 divided by 60, which is a beautiful division, you can just do your division inside there if you want to, right? If they give it to you in radians and it's some crazy decimal, then you're going to want to make sure that you are in radians, right? If they start out without the pi, because then it's going to be a weird conversion. But always make sure as we're going through this that you are at least in the right degrees versus radians, okay? So this guy is in minutes and seconds. How do I know that? Well, a little dash, right, tells me I'm in minutes and seconds. So all I personally would do is I would say the cosine. Make sure, by the way, you're in degrees. That is important, all right? So you may have to convert from degrees to radians, or you may have to do a conversion, pi over 180, 180 over pi. But make sure you are in degrees versus radians. But once you're in degrees, this is just going to be 26 plus, remember when we're converting the other way, divide. Like if you do that in your calculator, you'll get the same thing as if you go in and change it to minutes and seconds and then put it in like this. I personally would do this before I went into my menus, okay? And you should get the same thing. I believe when you do this, you get like, I want to talk about inverse trig functions because some people, sometimes when you're talking about inverse, you're going to talk about your reciprocal, but that's not what we're talking about. Reciprocal functions are like sine compared to cosecant. Inverse functions is when you're trying to find the angle. So on your calculator, you have your sine, cosine, and tangent. That's when you're trying to find the ratio, okay? Above it, you see sine to the -1, cosine to the -1, tangent to the -1. That is not your reciprocal function. That is your inverse function, which actually means you have your trig function and you want to find your angle, okay? And so this this chart right here gives you a 30-degree triangle, right? 30, 60, 90. So if I had two of these, I could say I need to find out what this is, and I could put the 0.5 into my calculator and use my inverse sign, and I would get 30 if I was in degrees, and I would get pi/6 in decimals if I was in radians. But that's when you are finding the angle. It's not when you're finding your reciprocal function. It's when you're finding your inverse. I want to go back and find my angle. All right. So here, solve A, B, C. This is a term that you will see. Solving a right triangle means I want every side and I want every angle measure. Now they've already given me one angle measure. The side's easy if they gave me two sides. What do you think I'm going to use to find my third side? Pythagorean theorem, right? So Pythagorean theorem's pretty straightforward. This is also a perfect triple. So if you use Pythagorean theorem here, it is going to be a 5, 12, 13. So this is a perfect little guy here. He's not going to be a decimal. They want me to solve every angle. One angle I know, it's what? 90 degrees, right? Because it's a right triangle. The other ones I can back into using my trig functions, all right? It says to the nearest 10th of a degree, which means your degrees in one decimal place. If I want to find alpha, so if I want to find alpha, I can say, well, the sine of alpha should be opposite. That's 5 over hypotenuse. That's 13. This is where you're going to use your inverse functions on your calculator. So you're going to say, well, then if I know what my sine is, I'm just going to put that in like this, right? And you will get, when you round it, hopefully 22.6 degrees. If not, check and make sure you're not in radians. There are two ways to find the other one. Now I have rounded this, but what do all of my angles add up to? 180. So there's two ways to do this. I can actually do the same thing I did here for beta, and I can say, oh, well, that's going to be 12 over 13, and you will get approximately, what, 67.4? Or you can use your 180 minus, I already know the 90, and the 22.6, right? Either way, you're going to get 67.4. Solving practical problems requires the use of angles of elevation and depression. Just like it sounds, elevations when you look up, it's all from the point of view, all right? Point of view. If you are looking up, that is the angle of elevation. If you are looking down, it's the angle of depression, and it is always to the horizontal. So if you were to look straight ahead and up, that angle that's created is angle of elevation. If you were to look straight ahead and down, that is angle of depression, all right? And so it's key that you know who is talking and what their point of view is, because it will change your problem. I will say, though, that if I am at the base of a mountain looking up, my angle of elevation will be the same as person at the top of the mountain looking down, the angle of depression from their point of view. So those will always be equal, because you can create this rectangle, right? And you can change it if it's easier to do it one way or the other. So let's look at the problem. Tyler views the peak of the Grand Teton from the Phelps Lake at an 11-degree angle of elevation. After kayaking 1.5 miles towards the Grand Teton, the angle of elevation is 14 degrees. Calculate the peak's height above the lake to the nearest foot. To the nearest foot, all right? So what never changes? Well, the height of the mountain. Clearly the height of the mountain is not changing, right? So we're going to use everything in relationship to this, all right? So when they said he kayaked, it's from his starting point here. So his total distance here is going to be the distance that he ends up being plus that 1.5 miles, right? So we basically have two triangles that are created here. The first one we're going to say is this 11 degrees. The sine of 11 degrees, right, should equal we're going to use tangent actually because we don't know our hypotenuse and I don't want to calculate it. So we're going to use tangent. So the tangent of my 11 degrees, that's this first triangle, should equal my opposite, that's height, over my adjacent, which is the x plus 1.5. Correct? So far, so good. Then we have the next triangle. The tangent of the 14 degrees should equal the height over the x. I have multiple variables. I don't want multiple variables. How do I solve this? Well, personally, I would use substitution. I would say isolate a variable, and then they're equal to each other because the height never changes. So isolate the height up here. If I isolate the height for this guy, I'm going to multiply both sides by this group, right? Everybody agree with that? So up here, the height equals the tangent of 11 degrees times x plus 1.5, right? If I isolate the height here is going to equal the tangent of 14 degrees times x, right? So far, so good? So tangent of 11 and tangent of 14 are actual numbers. I know they look like we don't know what we're talking about, but we're down to one variable. Because if the height never changes, what can I do with these two? They both equal h. Substitution says I can set them equal to each other, right? And so that's what you're going to do. You're going to say, well, the tangent of 11 times x plus 1.5 equals the tangent of 14 times x, right? You're going to want to distribute here to get that out. So tangent of 11 degrees times x plus 1.5 times the tangent of 11 equals the x times the tangent of 14, right? X is to one side, variables to the other. So I'm going to move that over. X tangent 11 minus x tangent of 14 equals 1.5 tangent 11. Factor out my x, right? So if I factor out my x, I get tangent 11 minus tangent of 14 equals 1.5 tangent 11. Divide by the group. Yeah, so this is negative, by the way. Divide, so x equals this guy divided by the group. And you can put that all into your calculator. You will have to do parentheses. And when you do trig functions, it will naturally open parentheses. So make sure you close those too, okay? So in your calculator, you can say negative 1.5 times tangent 11. It will open parentheses, close it. Divide, parentheses, subtract, close parentheses, okay? So x equals approximately 5.306. You can use your answer key. We are actually looking for the height. So you need to come back up here and figure out your height. So your height is going to be, as we said right here, tangent of 14 times that x that we just found, which gives you a height of approximately 1.323 with some decimals. That is in miles, and they want it in feet. So you do need to multiply that by 5,280 feet in 1 mile, which gives you, to the nearest foot, 6,985 feet.